So we're almost done with the hydrosphere. We just have one more section or one more unit left. And that would be oceans and coastlines. And again, if you have the book, this is chapter 13 in the recommended textbook. So what I'll say is that this first lecture is going to be the longest one, and then the other two will be a little bit shorter. There's more quiz questions in this lecture than normal, so just keep that in mind as you're going through. All right, so just to start out, just to remind you, so for the other two parts of the hydrosphere we've looked at, we have talked about the distribution of water on Earth, and we know that oceans cover 2/3 of Earth, but also 97% of water is salt water. So if we look at Earth from outer space, it's the blue planet, so we see much more water than we do land. So, what's interesting about the oceans is that the oceans are still a mystery to us. There are still organisms that get discovered and named every year that science has not known up to that point, which is pretty cool. So, there's like a list if you wanted an article assignment to do or a suggestion for an article assignment, you could look up some of the new species that have been named in the ocean in recent times. So, there's cool organisms that we didn't know existed that we're still learning about today. So, oceans are dynamic. I want to say that up front. Here at the university, we have an entire course just on oceans. It's called oceanography. So, again, I'm condensing everything down into 3 lectures that you could take an entire semester about. So, the reason that oceans are dynamic is because they're constantly in motion. There's the rotation of Earth that drives movement in the ocean, there's gravity, there's wind, which creates waves. There's also chemical changes that happen in the ocean. There's the heating of the ocean surface due to climate change. And then there's sea level and tectonics and climate. And there's a whole bunch of things related to oceans. So that makes them dynamic and they change constantly. So I just want to point that out, that oceans is a huge subject that we're condensing down to 3 lectures. So, for example, if you've ever been to the coastline, even especially here on Massachusetts, there's a tidal range. So you can go at high tide versus low tide. So we have 3 different locations here showing high tide versus low tide, high tide versus low tide, and high tide versus low tide. So we know even just on a day-to-day basis, if you're in a place like Massachusetts, there's 2 high tides and 2 low tides every day. So if we look at ocean basins, we know, or we've already talked about the fact that oceans, there are certain features on the ocean floor that are associated with tectonic plates. So the deepest point in the ocean is about 7 miles deep, and that's at the bottom of the Marianas Trench. Just for comparison, the Marianas Trench is deeper than Everest is tall. So on average, though, the ocean is about 2.3 miles deep. So I just want to point out this, if you know who James Cameron is, that's the person that made Titanic and Avatar. So James Cameron is really interested in oceans, and he went down to the bottom of the ocean in this submersible. So this is just kind of showing you an example of his submersible, the Deep Sea Challenger. So some of this stuff we did talk about back in plate tectonics. I realize that there's been a lot of content and a lot of material since then. You're probably overwhelmed with all of the material that we've gone through. So I just want to remind you that if we talk about the ocean floor, instead of using the word topography, which is like the elevation on the land surface, we use bathymetry. So if you take a bath, you're in the water and it's telling you how deep the ocean floor is. So this map here that we have is showing you the depth of the ocean floor, and we call that bathymetry. So just to remind you, there's some features on the ocean floor that we had talked about before. We talked about like the continental shelf. We talked about the abyssal plain. We talked about ridges. So there's a ridge right here, a mid-ocean ridge. And then we talked about trenches as well. So just to go through a couple of definitions here, or just to remind you that if you have what's called a passive continental margin, which that's written up here for you, a passive continental margin means there is no tectonic plate boundary at that location. So Massachusetts is an excellent example. We don't have a plate boundary nearby, so our coastline looks very, very different than if you're on the West Coast or if you're over by Japan or somewhere like that. In terms of what the features look like on the coastline. So let's say you're in a passive continental margin with no plate boundary. Basically, you'll be on the edge of the coastline, and then you have the continental shelf just off the edge of the beach, and then it'll go down to a slope, and then end up or terminate in the abyssal plain, which is about 2.5 miles below the surface. If you are on the west coast, then you might be on an active margin. So if you are on an active margin, that means that there's a tectonic plate boundary, and usually it means convergence. So you have two plates that are colliding, and one is going underneath of the other one. So you might have like an Andean type one. So on the west coast of South America, you got an ocean plate going underneath of a continental plate. That will make the coastline look very, very different than the East Coast beaches that we have here. Same thing if you're over on the western part of the Pacific, you have two oceans that are colliding and you get different features that will form. Okay, so based on that kind of brief recap of the features that we looked at, you could also go back to the plate tectonics one and try to look at the features in that lecture if some of this stuff is confusing to you. So I put all of these quiz questions in order here, so you have all of them here, questions 1 through 8 on your quiz. And those are going to all be based on this diagram that you have here, where you're trying to identify what these different features are on the ocean floor. So feel free to pause again and come back when you're done with this quiz question. Part 2 of this lecture is chemical properties of the ocean. So we're going to talk about like why the ocean is salty, what's the pH of the ocean, what's the salinity, what's the temperature of the ocean. So if you've never taken chemistry, or if you need a kind of a reminder about chemistry in the pH scale, pH goes from 1 to 14. It's a measure of how acidic or how basic something is. So if a pH is 7, that's neutral. That's what pure water is. If a pH is less than 7, it's acidic. And the lower or the closer it is to 1, it's more acidic, it's stronger. And if you go up to 14, so greater than 7 is basic, or what we would call alkaline. And the higher the number, the stronger the base is. So everyday products, or maybe not everyday products for everybody, but if you have an egg, for example, it has a pH of 8, bleach is a pH of 12. So those are basic or alkaline. Tomato juice is like a 4, coffee is like a 5, lemon juice like a 2, and then in your stomach, gastric acid is a pH of 1, so highly acidic. All right, so if we're talking about the pH of the ocean, on average, the pH is 8.05, but it does differ. So we'll look at a lot of maps over the next couple of slides. But if the colors are more purple, then that tells you the ocean is a little bit more, slightly more acidic. And if it's the red and greenish yellow colors, those are areas where the pH is a little bit less acidic. All right, but on average, the entire ocean is still basic because it is greater than 7. But the ocean is changing. So the ocean is actually becoming more acidic with time, and we'll talk about this again when we have climate change next week to finish up the course. So over time, the ocean is becoming more acidic, and that number keeps dropping. This is called ocean acidification, so it's becoming more acidic over time. How this happens is that if there's excess carbon dioxide, CO2, in the atmosphere, that CO2 can dissolve into the ocean, and then CO2 basically goes through this process where it can combine with water and form carbonic acid, which is H2CO3. You don't need to remember that, but the takeaway is that the ocean becomes more acidic over time. So we have a timeline here from October 1988 to October 2012. And in that amount of time, the pH has dropped from 8.12 to about 8.08 based on this graph right here. So that might not sound like much, but acidity is on a log scale. So every time you go up, it's kind of like earthquakes. You're increasing a magnitude of 10 if you go from a pH 8 to 7. Okay, so questions 9 and 10. So is the ocean acidic or basic on average? So you got to refer to the map 2 slides ago to look at the current ocean pH, or if you were listening to me, then you already know the answer. And then do a little research about ocean acidification. So why is ocean acidification a problem? And then how does it affect marine life? All right, and then I put some silly images on here. All right, so feel free to pause and then come back when you're ready. The next thing we need to talk about is salt. So we know the ocean is salty, but what do I mean by salty? So salinity is a measure of the concentration of salt in seawater. Typically it's measured as a percent, but we can also measure it as parts in 1,000 parts. If you have 1,000 parts of water, how many of them would be salt? So the average saltiness of the ocean is 3.5% salt, or that's 35 parts. If you had 1,000 parts of water, 35 of them would be salt in that concentration. So, what is salt made of? I don't just mean sodium chloride in the traditional sense of sodium here and chlorine here. There's other stuff dissolved in water, and where it comes from is when rocks break down in weather, it releases elements to the environment, and those get dissolved in water and then go to the ocean, make the ocean salty. So there's sulfur dissolved in water, there's magnesium dissolved in salt or seawater, there's calcium, there's potassium, and there's a bunch of other things dissolved in water. So here's a table on the right side that just shows you all the different things that you can find dissolved in ocean water. All right, but all of that together combines to give the ocean about 3.5% salt on average. So if we look at another map, this is a map of salinity. So the units here are parts per thousand. So 36 parts per thousand is the orange colors, and then 31 parts per thousand is more the blue colors. So if you're looking at this map, what you should notice is that the reddish colors are at like 30 degrees north and 30 degrees south on this map. And then the lowest salinity, so the more fresh water, is located in the Arctic. So our blue colors up here tells us that water is less salty up in the Arctic. So, your question based on that map, I want you to hypothesize and explain why ocean water is more salty near the equator and less salty at the North Pole. If we look at depth, so if you go below 500 meters in the ocean, so if you took a submersible down and you go below about 500 meters, ocean salinity becomes pretty uniform. So it'll kind of, if you have different areas on the surface that are either more salty or less salty, as soon as you go below 500 meters, it's all the same. It's usually the same salinity. So why is that? If you have salt water is more dense and it will sink. And the reason for that is because the more salty water is, the more stuff that is dissolved in it, the more mass it will have. So higher mass, more salt, more dense water, things that are dense, they tend to sink. What this graph is showing you is that if you have ocean water salinity in the summer, this is telling you at like the North Pole, for example, the surface water tends to be a little bit more fresh in the summer. And then as you go deeper, it gets more salty. So we're looking at low salt, high salt, and then this is depth below the surface. So as you follow North Pole, it's more fresh at the surface, it gets more salty with depth. But if you're at the tropics, it's more salty at the surface and it's less salty with depth. So the point here is that salinity, or how salty the ocean is uniform below 500 meters, but also that salty water, the more salty it is, the more dense it is, so it's more likely to sink down to the bottom of the ocean. All right, if we look at temperature, so if we have a map here of temperature, the warmest temperatures in the ocean are going to be right at the equator. The sun hits the equator most directly, so it's going to heat it up the most. If you're north or south of the equator, there's less temperature. It is colder because the sun does not hit those areas most directly. So orange colors represent warmer colors, warmer temperatures. Blue colors represent colder temperatures. Equator has the highest temperature. Go north or south of the equator, then you have colder temperatures. So just for some statistics, on average at the equator, it's about 81 degrees Fahrenheit. At the North and South Pole, it would be right near freezing. Similar to salinity, if you go down in the ocean, once you get below a certain depth, about 1,000 meters, so it'd be like 3,300, 3,400 feet. Once you go down that far, which is slightly over a half mile, then the sunlight doesn't hit down there, so the temperature is pretty uniform, and it's usually about 4 degrees. The average temperature of the ocean water is about 4 degrees Celsius. So the colder water is, the more dense it tends to be. Just like cold air is sinking air and warm air is rising air, water is the same way. Warmer water rises, colder water sinks. So cold water is more dense, and it will sink down to the bottom of the ocean. Warm water is less dense, and it will rise. And then again, what this figure is supposed to show you, we have basically Earth from, here's the equator, South Pole, Antarctica, North Pole, in the Arctic, and it's showing you with depth. The blue colors here represent the fact that the ocean water is about the same temperature as you go down about 3,300 feet or about 1,000 meters. It doesn't matter where you are, the temperature would be the same. So to put everything together, density is a measure of mass over volume. So things that are more dense, they're going to sink, and then things that are less dense, they will tend to rise or float. So the reason that Squidward, for example, here is bobbing up and down in this ice cube is because the ice is less dense than the liquid water. Same thing as an iceberg. So the iceberg ice is less dense than the liquid water, so it floats. So when we come back to density, there's a couple relationships here. So the more salty water is, the more dense it is. So if you have salty water, it's going to sink. If you have fresher water, it's going to float. Temperature has an inverse relationship. So as you increase density, temperature is going to be dropping. So cold water is more dense, warm water is less dense. All right, so at this point, you should be able to finish the quiz. You have 2 questions left, so you're going to answer the 2 questions about density.